Alright, everyone, Assalamu alaikum. This is Talha bin Nadeem, and today I am back with with the second video for the topic of the engine emissions and their controls. So, in the last class, in the last video, we basically studied that why these emissions are being produced, and we studied that these emissions are produced as a result of a combustion process, and these emissions are then exhaust into the atmosphere, which basically pollutes our environment. And we also discussed that these are some of the causes which occur because of these exhaust gases. Then we discuss some of the major causes of these emissions, that such emission occurs because of the non-stoichiometric combustion and dissociation of nitrogen, and we also said that because of the impurities in the fuel and air. After that, we studied that what type of emissions are basically occurring during the combustion process. After that, we also discussed that what should we do regarding the control of such emissions, and we discussed that either we will after treat our exhaust gases, or we may reduce the production, the generation of the emissions in the cylinder. And we also discussed that for after treatment we can use thermal and catalytic converter and particulate traps, and for inline reduction of emissions, in cylinder reduction of emissions, we can use exhaust gas recirculation system, and we may have some fuel additives for that purpose. And I also mentioned that we are not concerned with this part of fuel additives which are being employed to reduce the generation of the emissions. Then we discuss some of the basic history of the air pollution due to the IC engine. After that, we also discussed the Euro norms and the European standards. We also go through these Euro 1 and Euro 2 norm graph, and after that we basically discuss the classifications of the engine emissions, and we classified our emissions into two categories. First is the exhaust emission, and the second is the non-exhaust emission. And we said that exhaust emissions are basically those emissions like unburned hydrocarbon, oxides of the carbon, sulfur and nitrogens, some particulate, soot and smoke, while non-exhaust emissions are like fuel tank, carburetor, crankcase blow-by losses. So such are the losses due to the non-exhaust emission. And then we briefly discussed this graph, which is basically between the equivalence ratio, fuel air equivalence ratio, and the amount of the emissions which is being produced during the combustion process. And this graph is basically for CI engine. Then we studied the next graph, which is regarding the emissions of the which is between the fuel air equivalence ratio and the emissions which are being produced, but this graph is for the CI engines. Then at the end of the previous video, we discussed in quite some detail some of the causes because of which hydrocarbon emissions are being generated in CI engine, and these causes were incomplete combustion, crevice volumes, leakage past the exhaust valve, valve overlap, and the deposits on walls. And in the last we also discussed the oil on the combustion chamber walls. We discussed such things, these causes, quite briefly in the last video. So now moving forward towards our today's topic, we will start off with the hydrocarbon emission, with the causes of hydrocarbon emission, but this time in a two-stroke engine. So as I discussed earlier that in two-stroke engine, what we are basically doing, scavenging is done because of the presence with the help of the deflectors which are present on the piston, on the crown of the piston. And so what happens during the scavenging process is that when the fresh air fuel mixture comes into the combustion chamber, it pushes the exhaust gases towards the exhaust port and pushes those gases out of the exhaust port. And not only that, but after that it during this process, some of the fresh air fuel mixture also goes through this exhaust port, and this is a pure loss of the hydrocarbons. And such is the main reason, such is one of the reasons because of which hydrocarbon emissions in two-stroke engines occurs. So the intake air fuel mixture is used to push the exhaust residual out of the open exhaust port, which is called scavenging. So when this is done, some of the fresh air fuel mixture along with the exhaust gases are being expelled out of the cylinder before the exhaust port closes. So this is the major source of the hydrocarbon emissions in the exhaust. Most of two-stroke engines use crankcase compression. Now this is the second disadvantage, second reason for the emission of the hydrocarbon in two-stroke engines. So since we have a crankcase compression, therefore inside the crankcase we basically usually have the lubrication oil, but in two-stroke engine we do not have a lubrication oil, since we are compressing inside the crankcase. So how does the lubrication in two-stroke engine occurs? So what happens in the two-stroke engine, that we basically add some little amount of the lubrication oil in the fuel, and that amount is approximately about 2 to 3%. So this 2 to 3% amount of fuel is being added, of lubrication oil is being added in the fuel. So and it is being mixed properly, and so what happens, that when this fuel and oil mixture goes into the crankcase, during the compression process, when the piston is coming down, it will compress the air fuel mixture, and not only that, but it will also but the fuel particles, oil particles, will basically lubricate the components, lubricate the piston and cylinder walls. So this is how the lubrication in two-stroke engines occurs. So what happens because of this lubrication oil, when the fuel goes into the combustion chamber from the crankcase, so it will take some particles, some drops of the oil with it, and since oils are made up of a lengthy carbon chain, so what will happen as a result? They will not completely combust, and as a result we will have the production of some unburned hydrocarbon emissions. So this is what is happening. This is the second disadvantage, second main reason, second main cause for the production of the hydrocarbon emissions in the two-stroke engines. Next we have the hydrocarbon emissions in CI engines. So in the last video we started off with the hydrocarbon emission in SI engine. Then today we discussed the hydrocarbon emissions in two-stroke engine. Now we will start off with the hydrocarbon emissions in the CI engines. So CI engines, what happens that we only send the air in the intake during the intake process, and because of that intake air, only intake air is being compressed, and since the intake air is compressed only, therefore high compression ratios are used in the CI engines. So and when the fuel is being injected, then we usually have a very lean air fuel equivalence ratios, and because of this lean equivalence ratio, the production of the hydrocarbon emission is almost 1/5 of the emissions which are being produced in a SI engine, because in SI engine air fuel mixture is being taken into the is being sent into the combustion chamber for compression. The components in the diesel fuel have higher molecular weights as compared to the gasoline, and this results in higher boiling and condensing temperatures as well. And because of this higher condensing temperatures, soot formation is more in CI engines. So some of that hydrocarbon particles condenses on the surface of the cylinder walls, and a solid carbon soot is being generated during the combustion process. So this solid carbon soot is then being released into the atmosphere when the exhaust stroke occurs. So the hydrocarbon component condenses on the surface of the carbon particles. In addition to the solid carbon particles themselves, it also contributes in the emission of the unburned hydrocarbon emissions. Means not only these solid carbon particles are being deposited on the cylinder walls, they are also absorbing some unburned hydrocarbon emissions when during the compression process, and when the power stroke occurs, the pressure inside the cylinder chamber inside the combustion chamber reduces. Then this absorbed unburned hydrocarbon will then move back again into the combustion chamber, and it will not take part in the combustion, and it will be released into the atmosphere unburned. Therefore it is also so soot formation is not only the formation of the carbon, it is not only the pollutant itself, but it is also generating, it is also enhancing the it is also contributing the hydrocarbon emissions as well. So this is what is happening, what usually happens in the CI engine. And now moreover, so usually in CI engine combustion efficiencies of about 98% occurs, means only 2% of the hydrocarbon fuel is being emitted, which is quite less. So it is important that injectors are constructed in such a way that the injection stops such that there is no dribbling. So as we discussed that there should be no dribbling in the nozzles in the chapter number in the mechanical injection systems, that there should be no dribbling in the fuel in the fuel injection nozzles. But however, some amount of the liquid fuel is usually traps inside the tip of the nozzle, and when the piston is moving downward, when a suction pressure is generated inside the combustion chamber, that fuel from the nozzle is being driven into the combustion chamber, which will cause the increment in the hydrocarbon emissions as well. So that volume of fuel is called sack volume, means the volume, the amount of the fuel which is being present after the fuel injection, or inside, which is being trapped inside the fuel nozzle, on the tip of the nozzle. It is very small amount, but it will increase the hydrocarbon emissions. So the nozzle designs are of quite important, and it should have a minimum sack volume, so that we do not have the hydrocarbon emissions in CI engines. So not only because of the above three mentioned reasons, but some of the reasons of the hydrocarbon emissions in CI engines are almost same, like wall deposit absorption, oil film absorption, and crevice volume, etc. Now moving forward, we basically we will discuss some of the types of the emissions which are being generated, starting off with the formation of the carbon monoxide. Now carbon monoxide is basically a colorless and odorless gas, but it is a poisonous gas, and if a human being generates it, it will basically react with the oxygen which is taken in by our during the respiration process, and it will not allow the necessary reactions which are required inside our body, because that oxygen is being consumed by that carbon monoxide. So it is quite harmful from the human health point of view. So typically an SI engine consists 0.2 to 5%. Emissions of an SI engine consists 0.2 to 5% of the carbon monoxide in it. So it is an undesirable emission, and we do not want this emission. And not only that, it is an undesirable emission, but it is also the loss of a chemical energy, because we can convert this carbon monoxide into the carbon dioxide and then get a heat which can be utilized in doing some useful amount of work. So it is also a loss of energy. So when the next question is that when the formation of the carbon monoxide occur, or why the formation of the carbon monoxide occurs. So the answer to that question is quite simple: when we have a lesser amount of oxygen during the combustion process, in such cases the formation of carbon monoxide increases. So we can say that the maximum carbon monoxide is generated when the engine is running on a rich mixture, because we will have incomplete combustion. So even not only that, but even if we have a stoichiometric ratio, or even if we have a lean mixture as well, then in CI engines, some engines, we cannot assure that the mixture is being produced is purely homogeneous. So because of the poor mixing, because of not a good mixing, we may have the formation of the unburned, we may have the formation of the carbon monoxide as well, even if we have a stoichiometric or lean mixture. But in rich mixture, since we have a lesser amount of oxygen, then it is for sure that carbon monoxides will be formed. So since CI engines usually operate in overall lean conditions, so they have a very low carbon monoxide emissions. Now when we talk about the nitrogen oxide emissions, so as I mentioned earlier, that nitrogen oxide emissions occur when we achieve the maximum flame temperature, when the cylinder temperatures are quite high. So an exhaust gas of an engine can have up to about 2000 ppm of nitrogen oxides. most of that will be of nitrogen monoxide, but there can be some particles, some molecules, some amount of the nitrogen dioxide as well. So NOxes are basically undesirable, and as I mentioned earlier that it can cause the acidic rain as well, and not only that it causes the acidic rain, but it can lead to the formation of the smog and will lead to the damage of the ozone layer as well. So at low temperatures the atmospheric nitrogen exists as a stable molecule, means it exists as a N2 molecule, and it will not make the nitrogen oxides. But when we have a very high temperatures inside the cylinder, then this nitrogen molecule will break and oxides will be formed, and so it is completely undesirable. These pollutants are completely undesirable. So the highest concentration of the nitrogen oxide is around the spark plug, where we usually have a highest temperature. And not only that, if we have a spark timing in advance, the cylinder temperatures will be increased and more NOxes will be produced. So next we have a photochemical smog. As I mentioned earlier that I will explain the formation of the photochemical smog and how nitrogen basically affects the ozone layer. I will discuss this later. So now I am going to start off that part, that what happens in the photochemical smog is that when the sunlight, this nitrogen dioxide molecule is being attacked by a sunlight, rays from a sunlight, it will provide a necessary activation energy to remove this oxygen, this monoatomic oxygen, and nitrogen oxide and smog will be produced. And this monoatomic oxygen will react with the oxygen molecules and it will produce ozone, it will form ozone. So ozone, and humans basically cannot survive, cannot inhale ozone, because it is a harmful gas on the ground level and it can damage our biological tissues, and not only from the human's point of view, but it is also harmful for the plants and trees as well. So we do not want the formation of ozone on the ground level, but nitrogen dioxide causes the formation of the ozone. So that is why these emissions have to be controlled. They are completely undesirable. Now moving forward, we have a particulates. Again, as I mentioned earlier, that particulates are not a main cause, are not a main pollutant in the SI engine, but in CI engines, since the exhaust of CI engine contains solid carbon soot particles which are being generated particularly where we have a rich air fuel mixture zone. So some of those particles are being released into the atmosphere during the exhaust process, and they are undesirable and odorous pollutants. So maximum density of a particulate emissions occur when fuel is injected to the maximum power, means we have a rich air fuel mixture or we have a poor fuel economy. So soot particles are usually in the form of a cluster of solid carbon spheres. These spheres are of usually diameter range from 9 to 90, but most of them are within the range of the 15 to 30. The spheres are solid carbons with hydrocarbon and the traces of other components absorbed by the surfaces, means it will not be the hydrocarbon, it will not only be the carbon, but it also contains some hydrocarbons with it, because that soot formation, that particulates which are being deposited on the wall have absorbed some amount of the hydrocarbons. Now next we have the formation of the aldehydes. Aldehydes are the major emission problem when we are talking, particularly when we are talking about the alcohol fuse. And the formation of aldehydes is completely undesirable because it is an eye and respiratory irritant. This is a product of incomplete combustion, means when alcohol is when incomplete combustion in alcohols occur, aldehydes are formed, and this is one of the major problem with the usage of the alcohols as a fuel. But since the alcohols are not being used in that much amount as the petrol, gasoline has been used, therefore the emissions, such emissions are not a problem for now at least, but in future it may be a problem. Now next we have a lead. Long before, as I mentioned, that a component which was known as the tetraethyl lead was used for the increment of the octane number of the fuel, and this led to the release of the lead in the atmosphere when the combustion occurs. So and when the humans inhale it, it causes cancer, and it basically affects various organs of the humans as well. Therefore nowadays it has been banned, but as you can see that in 1920s tetraethyl lead, use of the tetraethyl lead was started, and up to 1980s it was still operational. So mostly emitted from gasoline additives, battery factories and non-ferrous smelters. Now this has been removed because in gasoline it is not being used as an additive now. So now moving forward, next we have the formation of the sulfur oxides. As I mentioned earlier that sulfur formation of the sulfur oxide causes is one of the major reason for the acidic rain, and a fuel may contain, a gasoline contains about 150 to 550 ppm of a sulfur by weight, but diesel fuel can contain up to 5500 ppms by weight. But in some developed countries this has been reduced to a tenth value of this, means only 550 ppms or maybe 300-400 ppms are being allowed. So what happens at higher temperatures, sulfur combines with the hydrogen as well, and it produces hydrogen sulfide. Again, this is a toxic gas, and oxygen when combines with the sulfur, it produces sulfur dioxide. Again, this causes the formation of the acid rain. Now when an engine exhaust can contain up to 20 ppm of sulfur dioxide, then combines with the oxygen to form sulfur trioxide, and when these sulfur trioxide and sulfur dioxides are combined with the water vapors, when sulfur trioxide combines, it forms sulfuric acid and causes acidic rain, and when sulfur dioxide combine, it produces sulfurous acid, and this is also another reason reason for the acidic rain as well. So sulfur is basically the main threat here, and it has to be a lot of work has been done recently to minimize the amount of the sulfur from the fuel. So in many countries many countries have laws restricting the amount of the sulfur allowed in the fuel. they are continuously being made more stringent. During the 1990s, the developed countries reduced acceptable level of sulfur from 0.05 to 0.01 percentage. Sulfur, the amount of a sulfur in natural gas can be ranged from little to large. This can be a major emission problem when natural gas is used in IC engine. Okay, and now starting off with the methods from which we can control the emissions in the SI engine. And as I mentioned earlier that we can do some different methods like after treatment of exhaust gases, and the other thing which I discussed was the improvement in the fuel quality as well. Now another thing which here we can do is the modification in the engine designs, and for that purpose today in today's class we will discuss this modification, and in the next video we will discuss the treatment of the exhaust gases, and we will not discuss the modification of the fuels here because we are more concerned with the IC engines, not the formation of the fuels. Now moving forward, we have the first modification in the design, and it is related to the combustion chamber configuration. And here you can see that we have to modify our combustion chamber in such a way that we have to avoid the flame quenching zones. It means we have to avoid such zones where we have incomplete combustions, and it will result in the higher formation of the hydrocarbon emissions. And we can do it by reducing the surface to volume ratio and by reducing the space around the piston rings. Next we have the lower compression ratio. That lower compression ratio will basically reduce the quenching effect, and by reducing the quenching areas, it will ultimately reduce the emission of the hydrocarbons. And not only that, but it will, since the compression ratios has been reduced, therefore NOx's emission, the maximum flame temperatures are being reduced, therefore NOx's emissions have also been reduced, but it will cause a reduction in the thermal efficiency and will also increase the fuel consumption as well. So this is a disadvantage of the using lower compression ratios as well. Moving forward, next we have the modified induction system. Means we, as I mentioned earlier, that we might have some issues when we are talking about the formation of the air fuel mixture, particularly that it is never ensured that the uniform or homogeneous mixtures has been prepared, or particularly when we are talking about a multi-cylinder engine, it can never be ensured that same amount of the air fuel ratio is going into the multi-cylinders. Therefore we have to modify our induction systems accordingly so that it will provide the desired same amount of the air fuel mixture for all load and power requirements. Next is the ignition timing. Now as I mentioned earlier, that when we are talking when we have an advanced spark, when we have an ignition timing set to the advanced, we will achieve the maximum flame temperatures, and when the maximum flame temperatures are achieved, formation of the NOxes increases a lot. So this is one of the main reasons here we cannot use so much advanced spark timing, otherwise the NOx's emissions will be increased. So NOx's emissions are reduced due to lowering of the maximum combustion temperature, and combustion temperatures are being lowered when we do not have an advanced spark. So NOx's emissions will ultimately be reduced. Also hydrocarbon emissions get reduced due to high exhaust temperatures. So however, when we have a high exhaust temperature, the cooling requirements will be increased, and fuel economy will also suffer to a extent and we will have some power losses as well. Therefore we have to balance that. Either we cannot have a too much advanced spark because it will increase the noxious emission. We cannot have a too much lower retard spark condition, otherwise it will increase the hydrocarbon emissions because of the incomplete combustion. So we have to do a trade-off between that. Next is the reduced valve overlap time. This is again where we in real engines there appears a condition when inlet valve and the exhaust, both inlet valve and the exhaust valves are open, and some of the fresh air fuel mixture which is coming into the combustion chamber is then being released into the atmosphere directly and does not get combusted. So it has to be controlled, it has to be ensured that such conditions does not occur, and for that purpose a new variable valve timing technology has been used, and it controls the opening and closing of the valves so that it is ensured that the valve overlap time has been reduced to the minimum possible crank degrees angles. So I think that's all for today. In the next video, in the third video of the emission controls, we will start off with the emission, with the exhaust gas control process, means the equipments which we can use like thermal and catalytic converters, afterburners, exhaust gas recirculation system, and particulate traps. So we will start off with those topics. Till then I hope you guys will watch this video very carefully and understand the basic concepts. If in case you have any question, any query regarding it, just note down your questions and you can ask me during the online session. So till then, Allah Hafiz.